Hi everyone, in this video we're going to go through section 28.4, basic trigonometric forms. We have yet another lovely section on integration. So that's kind of how we close out this course with various methods and techniques and different ways that we can integrate, and the emphasis is heavily on u substitution. Because we are talking trig in this section, I want to just review our trig derivatives, and that will help as we go through and try to think of our trigonometric antiderivatives. So we start out with the derivative of the sine of x is the cosine of x. The derivative of the cosine of x is negative sine x. And the derivative of tangent x is secant squared x. Right? Hopefully we remember those three, the three that are a little bit more challenging to remember. Now the derivative of cosecant x is negative cosecant x cotangent x. Then the derivative of secant x is secant x times tangent x, and the derivative of the cosecant of x, or excuse me, cotangent of x is equal to negative cosecant squared x. Right now, I know that your calculator can do all 6 of those, but as you go through the section, when you do the homework and do a test on the section, I want to at least see one step, especially that u substitution step. Now we look at our first two examples here. We have to integrate sine x and we have to integrate tangent x. It turns out that sine is much easier to integrate than tangent. So I only know the antiderivatives of the ones from the previous slide that are on the right, right? There is nowhere on the previous slide where it said that the derivative of blank is tangent x, right? So that one we've got to put a little bit more thought into when we do it. But we know from the derivative sections that sine and cosine flip back and forth. So if I just say that this one is equal to the cosine of x and then tack on my plus c, because I'm never going to forget that. What's really, really, really important here is to check with a derivative. Right? Check with a derivative, because you're better at derivatives. You've done them more frequently, and it's fresher in your brains. So if I take the derivative of cosine x, check back to the last slide, it is negative sine x. And then you say, hey, that's not what I started with over there. So how do I fix this thing? Well, I need to take and put a negative in my answer. So the antiderivative, the integral of the sine of x with respect to x, is negative cosine x plus c. So my suggestion is, well, use your calculator to support you, but always check with a derivative. It's going to make you miss that negative sign less frequently. All right, now, when we take and integrate tangent x, like I said, there is nowhere on that slide previously that had a tangent x on the right-hand side by itself. Okay, so what I'm going to do for this one, and you may see this problem again on a test, so keep this in mind, is I'm going to write the tangent of x as the sine of x over the cosine of x dx, because now this allows me to make a u substitution. And I think we even encountered one. Oops, I forgot my integral sign. I think we even encountered this similar problem in the previous section. Maybe it was a little bit different. In the previous section, I think 28.2, when we had lots of natural logs. So if I set u equal to the denominator, cosine x, and du is negative sine x dx, I can make my u substitution. That negative, I'm going to write over on the other side. Okay, so divide both sides by -1 is kind of the formal way that we think about that. And when I make my u substitution, the sine x dx is negative du. Okay, so I have the integral of, and I'll pull the negative all the way out in front, negative du, and then the cosine of the denominator is 1 over u. All right, so there's my substitution. Now, how do I integrate 1 over u? That is, keep my negative out in front, negative natural log of u plus c. Put my absolute value around that, and then that is negative ln of, absolute value, of cosine x plus c. So that second one, a little bit more tricky, a little bit more involved than the first one, okay? Cool. Next example that we get here, we got to integrate x secant squared x squared dx. So the thing to kind of key in on initially is I see that secant squared kind of sandwiched in the middle there. I know the integral of secant squared by itself is tangent x because the derivative of tangent x is secant squared x. Okay, so we'll get to that, but first we have to deal with the fact that we have an x squared in there and an x out in front, and we do that, oddly enough, with a u sub. So we're going to set u equal to what's inside of the secant, x squared, and then du is 2x dx. So the x dx I have right there, right? But not a 2, so I'm going to write that as 1/2 on the left-hand side. Okay, so when we make our substitution, this is equal to 1/2 the integral of secant squared u du, right? The blue box is equal to u. Okay, and then I can take my antiderivative, secant squared, the integral, the antiderivative of that is tangent. So tangent x plus c. Oh, nope, I made a mistake there. That is the tangent of u plus c, so that I can back substitute 1/2 tangent of x squared plus my constant c. And there's my answer for that one. Our next example involves another oddball, tangent 2x over cosine 2x dx. That's what we're integrating. And again, keep going back to that first slide, or if you wrote those down, keep looking at those 6 derivatives that we know or have in front of us. There's no relationship here between tangent and cosine. If I set like u equal to my tangent term, then the derivative of secant squared, I don't have a secant squared anywhere. If I set u equal to cosine, derivative of cosine is negative sine. I don't have that anywhere. So here's the, I don't want to say trick that we're going to use, but here's the approach we're going to take with this one. 1 over the cosine of x, that cosine in the denominator, that is the secant of x. So if I want to, in this problem, bring that cosine 2x up out of the denominator and write it as secant 2x tangent 2x dx. And I knew to do that. I knew to do that because I knew where this problem was going. Okay, now you've seen it once. Hopefully, like you might think to do it again on a different problem. But the reason this is beneficial is, or helpful to us, secant x tangent x, that has a nice antiderivative. The antiderivative is just secant. Okay. However, we've got to deal with this 2 in there, and I could do this as a u substitution. U is equal to 2x. Du is 2 dx, but ultimately I'm going to get a 1/2 coming out in front of my integral. Okay, so I'm not going to write the u step in this one. I'm just going to go right to this is equal to 1/2 the secant of 2x plus c. Okay, so the secant 2x, tangent 2x, they sandwich together to be secant when I take the antiderivative. I want to take one more quick look at that problem that we just did. This is the exact same problem. And I could have done something differently, right? Sometimes when I have tangents and sines and cosines all in the same problem, it helps to write everything in terms of sines and cosines and simplify. So let's see what happens here. If I write this as the sine of 2x over the cosine of 2x, because that's what tangent is equal to, over the cosine of 2x dx. How can I simplify this? This is over 1. So I can take now, and let's say that this is equal to sine 2x over cosine 2x times, so I'm rewriting this big division bar as multiplication and flipping the denominator over, 1 over cosine 2x dx. Now I've got my cosines both in the denominator, sine 2x over cosine squared, because cosine times cosine, 2x dx. All right, maybe that looks worse. Maybe it looks better, right? You might like sines and cosines better than secants and tangents. But the advantage here, or maybe not the advantage, the approach that we can take here is, again, a u substitution. And what you end up with is like 1 over u squared, which is du, which is u to the negative 2, right? Then that might be easier to integrate. So you can do these more than one way. Often there's one way that is most efficient, most convenient. You might run into like some hiccups in this one, but that's just something to be aware of. There might be more than one approach to some of these problems. We're going to look at one more example here where we're going to integrate cotangent x dx. And we did tangent earlier by writing it as sines and cosines. So let's do the exact same thing with this one. Write this as cosine x over sine x dx. And maybe take a second and think, which one should you set u equal to in this problem? Give you 2 seconds to think, and then I'll tell you which one u is. It's the one in the denominator. We're going to set u equal to the sine of x. We never wanted to see a du in the denominator. That doesn't work out nicely. U is sine x. Du is cosine x dx. And when we make our substitution, integral 1 over u du. That is all we're left with after the substitution, and that is equal to the natural log of u plus c. And when we back substitute, that is the natural log of sine x plus our constant c. Cool. So that's 28.4. A few more examples of integrals. Thank you for watching, and have a wonderful day.